Hello, I'm Mikhail, and in Yadro I'm working on software for storage appliances and primarily focusing on data protection layer and data integrity. And actually the whole talk is based on our experience in bringing up data integrity to our storage system. And it covers issues we faced with working data integrity on hardware level, on software level, on virtual environment, and so on. So to give more context, we are doing storage appliance. It's primarily block storage based on open power hardware with PowerPC Linux running inside. And currently we have more than exabytes capacity installed with hundreds of systems and run up to several petabytes in each system. And when you have hundreds of systems with thousands of drives, data integrity and data consistency become vital for you as you start facing hardware, software issues, and human factor, and so on. So somehow we need to ensure our data is correct and we don't read something wrong. Okay, so to be more specific, we have our own distributed RAID implementation, and we want to bring data integrity inside it. And we want to keep some additional metadata that helps us to detect stealth corruption, and it can be anything. It can be checksum, it can be reference, update numbers, whatever. It's just metadata. And we don't want to have some external metadata storage as it would bring up performance penalties, and we want to have something simple, to have something stored inside, next to the data, right inside these drives. Okay. And actually we started with some naive approach. We have disks that support extended sector size that allows to put some additional bytes next to logical block. And the idea was just get this logical block, store this metadata there, and we are good. Well, to start this, we just need to format drives. And after 16 hours, we find out that actually Linux doesn't work fine with standard sector size. What we can do about this is somehow to update SCSI disk driver to work with extended sector, but it's not something we would like to do. And our plan to store the metadata failed from the beginning. At the same time, the whole idea to store metadata next to data doesn't look crazy and somehow should be solved in modern world. And we start looking what exists in the industry. And about 15 years ago, everything was defined, standardized, and so on. And we have T10 protection info standards that defines protection metadata with fixed format data integrity field per logical block. And it defines how to store this data, what is content, and how to move it around the sun, and so on. So everything is in place. We just need to take and use it. So it looks simple. So, and in Eris, there is a data integrity field next to the user data, next to the logical block, and it contains 3 fields. And from our perspective, it allows to store up to 6 bytes per logical block. That looks good. And it also allows to store checksum. Just looks good as well. And the whole standard is quite flexible. We can have multiple integrity fields per logical block, but actually I didn't see if it works on any drives. We have. Okay, and from the kernel point of view, we have everything in place as well. So we have API to register devices integrity capable. We have APIs to attach protection metadata to the page and to the bio structure. And it supports custom metadata models that defines what metadata we can store, how we can verify, generate, and so on. And even, I believe, DM integrity have their own metadata, and T10 protection info is implemented as well. So that looks we have everything in place. We have hardware, we have kernel API support, and looks like we can do something with this. So in practice, first we need to do is to say that we want to format our SAS drive to something that have protection info. There is a nice utility called SG format that allows to specify block size, protection info, and so on. It's a bit strange, but and sometimes for some drives it requires 6-byte commands, for some 10 bytes. Some drives requires both of them depending on what block size you are using. For type 1 format, you need to say that PI info is 2. For 3, it's PI info 3, protection field usage 1. And why it's so strange, actually, it's because of SCSI block spec that basically it's 2. It's just reflection of SCSI block specification, block command specification. Anyway, what we found that no SAS drive supports type 3. At least NL SAS and some flash SAS drives doesn't support it, so we don't have 6 bytes of metadata. We have only 2 bytes of metadata. And after 16 hours of formatting, we found out that actually nothing happens. So we got a device with lower capacity. SCSI stack says that everything in place, but nothing changed. So Linux block stack says that it's still not integrity capable. It doesn't allow to store metadata, and actually nothing works. At the same time, SCSI says that it's good. It's type 1 protection. Store metadata there. Digging in some source code and on HBA layer, on SCSI disk driver, and so on, we found that data integrity should be enabled both on disk and on HBA layer, and by default, in our case at least, data integrity was disabled on driver side. So basically, data integrity was present on drive. It was generated by the HBA. It was stripped by HBA when we read data back, and we have integrity somewhere between HBA and disk, and it isn't visible to Linux kernel. It's good, but it's not what we want. Okay, and in our case, HBA required explicit diff enablement, and for Broadcom, we have to add protection mask that should enable data integrity field exposed to Linux kernel. And after this, we have protection for detected by Linux kernel, but we have still text size 0, so we can store metadata there. And to have the ability to store metadata, we need to update control mode page on SAS drive with this nice command. And after this, you get application tag enabled. And how we know that everything worked? Actually, everything was broken. So after all this manipulation, we have error on any request, read or write from HBA driver with some magic numbers that are not really descriptive. And we need to, actually, first we tried to update driver with the latest version from vendor, and it suddenly helped. The first idea was that we have some old driver in kernel, but then we compared the source code and found out that in kernel, you simply don't have a data integrity field support for this driver in upstream, but we have this on vendor driver. Why it's here, I don't know, and why upstream driver allows to enable data integrity field while it doesn't have a data integrity field, I don't know again, but driver from the vendor works fine. And altogether, if we can take correct drive with correct format, put a correct settings there, configure HBA correctly, and again get a right version of HBA driver, that works. We have a device that is detected by block layer, and it reports these nice numbers we would like to know. And we can read and write data, that's fine. With NVMe, it was much more simpler. It's protection info on NVMe drives are actually a copy of SCSI spec. It is optional. It can be configured per namespace, and we may have different namespaces with different formats. And Linux kernel also supports no profile for integrity, so it allows just to put some metadata with no, and drive doesn't care what is inside. But actually, we faced some issue with some drive models in complex setup, like when we have 2 ports on VMEs with number of namespaces configured, that some namespaces has protection enabled, others are without protection, and sometimes we get protection row from namespaces without protection, but maybe it was just a firmware issue with some specific drive. Okay, and as this thing is optional, it's basically available on some enterprise data center lines, model lines from different vendors, so it's not somehow consumer feature. And when we enable type integrity protection on NVMe, it looks like something like this. So device supports protection, it's enabled, and we have a logical block format that allows to store metadata there. And once we get our hardware working with integrity, the question is how can we do something with it. So we need to write some code, and we need to test this code, and we want to write code on laptop. And we can simply plug HBA with Gboard with SAS drives to laptop to develop. So we need some approach to emulate data integrity on top of general purpose drives or general purpose block devices to do some development. And in our case, Casa Target code helped us a lot, as it contains backend and frontend drivers that allows integrity protection emulation. So basically, SCSI Targets allows to configure SCSI backend, SCSI frontend, and get the whole thing together. And in our case, for backend, we can take file.io that presents a feature to emulate data integrity. And from the other side, we can use a loopback frontend that allows to get any backend as a local SCSI device. So altogether, we can get SCSI device on any hardware. And we get something like this picture. So we have a SATA drive with file system, with metadata and data files, with target core file, with on top of TCM look, and on top we get a SCSI block device with data integrity. And all this put inside virtual machine and run anywhere. Actually, it works better than nothing, but it's not perfect. We have found some issues regarding reference stack enforcement and so on, but it's really helped us to bring the whole thing up. And it's quite good for development. Another story is about testing. So we have our storage appliance, we have some code, and we want to test it in continuous integration and verify changes and so on. And we have 2 different stories. One, we need some local drive with integrity protection, and another story is to have some shared drives attached to virtual cluster to run integrational test inside virtual environments. And for the first case, we just took NVMe and put it as PCI device inside virtual machine. And as expected, it works fine, no issues. And the only thing is limitations that you can put it only in single virtual machine. And if you would like to scale it somehow, you need or dual port drives with some hardware that support dual port, or you can use SRV feature. And actually, we didn't see if it works in real life. But anyway, it works. Another story is for testing in virtual machine with virtual cluster and with shared drives. So in continuous integration, we emulate the whole system as virtual machines. So we have a number of virtual machines that see the same shared device. And we want this device to be with integrity protection. In the beginning of the slide, we got this picture with SAS drives connected to the host via HBA, and it looks like ordinary SAS SCSI disk with integrity protection. And we want to put it inside virtual machine. And here we can use the same approach as we used for emulation, but leverage vhost driver on host. So basically, we get a block device, put it inside target core block backend, and present it to the virtual machine via vhost SCSI driver. With this setup, virtual machine just see ordinary block device with integrity protection enabled. And as far as we found, it's on vhost and virtio SCSI. It's the only driver currently that supports that integrity pass through to virtual machine and anyway. At the same time, the only issue here that target core block can't share the same drive twice or number of times. So we can't put this target core inside multiple virtual machines. And we also can't put single vhost to multiple virtual machines, and we need to do something about this. But the good news is from 4.12, device mapper supports data integrity pass-through, so we can have multiple block devices on top of single SAS device, put it inside target core, vhost, and have multiple virtual machines sharing the same drive, and finally get our system C shared drive inside virtual machines and run some tests. And if we remember that we have SCSI disk attached to gbot, we can have this gbot attached to multiple hosts and have virtual machines on multiple hosts seeing the same SAS drives with all integrity features we need to emulate. And the only issue here was that that integrity doesn't work by default again. So both drivers seem to support integrity protection, and there is some code around this feature bit in both drivers, but by default it's disabled, and there was no way to enable it somehow. In fact, this changed in qemu 3.1, and in 3.1 we have this feature bit somehow published to qemu code, and qemu can now enable this feature bit, and with this we have protection for enabled both on host and virtual SCSI code. Okay, and libvirt, as far as I know, doesn't support this flag, but with qemu command line and extended in space, we can pass it to virtual machine. And how we find out that everything works? Actually, again, we have this feature flag negotiated, and we have integrity block integrity detected inside virtual machine, but again, we got errors on any request we sent to in virtual machine to block device. And we got a standard error black block number requested. That is usually happens when they have misaligned offset or length. And eventually we found that somebody stalls 56 bytes per each request. After a little digging up, logs, debug, and so on, we found that we have a 4K issue. This issue only happens with 4K blocks, and in virtual SCSI there was incorrect block protection for size calculations. After that, we find that somebody already fixed for us this, and it's really nice. We backport these changes, and eventually the whole thing works here. We also looked at SPDK to do the same structure as we used with target core, but in SPDK NVMe integrity looks good, but vhost SCSI doesn't support integrity, and actually to bring up the whole system on power was a pain, as it looks like nobody ever tried to run SPDK on power, at least for vhost applications. We somehow fixed it, but virt vhost SCSI still doesn't support integrity, and we put this SPDK thing away. Okay. In practice, we have the structure when we can write and read data, but when we start working with our software, we start getting block integrity errors almost on every request. Most of them related to logical block reference tag check failed that somehow hints that we have something wrong with reference tag. And obviously, it's only about type 1 protection. And in type 1 protection, according to spec, you need to have lower bits of LBA put inside reference tag. And every next segments of data should have this incremented by 1. But actually, for Linux block, it's kind of not tricky, but it took us some time to realize that when we are doing I/O on block device on type 1 on 4K, we need to put in the first segment LBA, but for the second and next segment, we need to increment it by 1, not by 8, to make the whole thing happen. So this is how it works for 50 half kilobyte sector, and that's pretty straightforward. And for 4K sector, it's kind of not so straightforward. And basically, we need to keep track of what logical block on our hardware and correctly remap this reference tags to have the whole BIO with correct reference tag sent to the device. Anyway, the next issue we get was related to large requests, and on virtio SCSI it's more than 126 64K page, and the first attempt was just to hardcode this limit and go forward, but the next we found that the same issue happens with NVMe drives with only 32 pages. And it was actually about scheduler and request splitting and this reference tag remapping thing, and basically we don't want, if we use integrity, we don't want our request to be split by scheduler to not mess with reference tags. And the other issue was only NVMe specific, and with NVMe you should have only single metadata page, so we have all metadata stored continuously on single page when you're doing PCIe NVMe drives, and it's somehow related to physical page rig and method of transfer metadata and data to the PCI device. And actually, it's reported in block integrity hints, and we can just need to look at it. Actually, I don't know why in block integrity in these Q hints we have max segment size is 33 pages, but actually, when you have integrity, you have only 32 with 1 page for integrity, but that's how it works. And in recent kernel, looks like we have agile support for NVMe drives, but we still have this limitation from the IO hints. And the last issue we faced was, again, on NVMe drives, and for some reason, when you have a segment size larger than 4K on 4K block device and on type 1 protection, you get protection errors from the device. And moreover, some devices got stuck, some get controller resets, and the whole system got stuck. So we have to limit this max segment size to 4K. And actually, it's not an issue for Intel platform, but on Power, we have 64K pages, and it's strange. Okay, and a few words regarding performance. As I said before, this integrity thing requires a Guard tag to contain checksum of data sent to device, and we have to use CRC16 to send request to the data. And in fact, default implementation for generic implementation for this in kernel is really slow on our hardware. It gets only 100 megs per second on single core tests. But starting from 4.12 and long time ago for x86 platform, and starting from 4.12, we have a nice factory implementation for power, and it works really nice for our hardware. So it's 2 orders of magnitude faster. Okay, so to wrapping up the whole talk, we managed to use block integrity inside Linux. We use it both on SCSI protection info and NVMe protection info in dual port drives, and it works fine. We found a way to put this thing inside virtual machines for testing, for continuous integration, and emulate the whole thing inside developer machines. Starting in device mapper works great, starting from 4.12 with protection info, and all above help us deliver our software with block integrity enabled. Still, we don't have any user space API to work with integrity. We have a limited support from the SPDKs we host side, but I think that's something that can be fixed in future. Thank you.
Thank you, Mikhail. Martin?
Hi. So I have a whole bunch of feedback to your presentation, but I don't think we have time for that. But in terms of your last point about userland API, finally got a guy working on that, adding PI support to IO Uring.
Great.
And so the hope is that sometime this summer, hopefully, we'll be able to port all the PI qualification that currently is tied into Oracle junk and make that something that works with IO Uring so we can add it to block tests. Also, in terms of the 4K ref tag issues and all that stuff, there are tests and block tests now, so hopefully the regressions we've had in that area have been fixed.
Great.
Oh, and the Broadcom driver thing, that's a known issue.
Actually, Broadcom driver, when you configure it right, it's great, it works. As it's actually the only driver that works for us, as other doesn't have it at all. So.
Yeah. Most people that currently use this are on fiber channel, right? And it just works there.
Oh.
Is that it? You wanted to slag off Broadcom too?
Yeah, basically. Oops, wasn't me.
Shameless fiber channel promotion?
Well, you said it. I wouldn't. So I would never do it. So, but no, Broadcom is horrible. I know.
So I had a question. So what about in practice? So once you kind of got rid of the false positives in the code and so on, what kind of fraction or what percentage of actual integrity check faults do you see in a real system?
Actually, the whole thing was about how we can improve our background checks and read-write path checks on data, and how we can ensure that data we read from the drive is correct and we don't have stealth corruption. And with additional metadata, we managed to, without little overhead, we can say that the data we read is is stale or is corrupted, and we can do online recovery and get correct data to the user. So basically, with additional metadata, we managed to solve this issue.
Yeah, so I'm asking, so in practice, so in a real system with a petabyte or with 10 petabytes, do you see faults, or with what frequency do you see faults?
Actually, not a lot. Maybe a few.
So not a lot, like
not a lot.
One per 10,000 or one per million?
Actually, I'm not ready to say some numbers.
All right, good, that's fine.
I do have another one. You mentioned something that you had issues with the 4K and blocks and request splits, so that you were sending down two large requests which were then split, and then the checksum wouldn't work anymore. That was on one of your previous slides there.
Actually, it wasn't about checksum, but it was about reference tags.
Yeah, the reference tag.
And
so, right. No, just that one there.
Mm-hmm.
So, how do you manage to get those large requests? Because by rights, it all should be set up according to the queue limits. And so the queue limits should be containing the correct values, allowing you to format correct requests, which then would not be split. So did you format the request incorrectly? Or was it somewhere in the stack so that we're not propagating the block limits correctly?
So initially, it was our fault as we didn't respect the block limits.
Yeah.
But with when we found that there is max segment sealed in queue and so on, and we started expecting it, we have a lot of issue gone, as expected. But for the NVMe driver, we still have some issue related that it reports that you can have 33 segments maximum of data sent to the driver. But if you have integrity enabled, it's only 32 with one integrity page. But it's somehow not aligned with SAS, SCSI stack. I don't know how it works. So basically, in our code,
that really sounds dodgy, and so there is an issue somewhere.
Yeah,
Not sure whether it's us or you, but it doesn't really sound very
Yeah, I
good.
think maybe.
Technically, the burden is on the submitter of the I/O to bounce the PI to fit within a page. The NVMe driver doesn't do that by default. But I don't know.
Hello, you want to?
Sorry. Like PI buffer bouncing, like we never did anything with that in NVMe. Oh, so we come to the NVMe? Yeah.
Yeah. All right, there you go. So you can, Mikhail, you can create the integrity buff, and the guys with high integrity here. There's at least 4 of them, right? I think as far as I detected. So, thank you.
Thank you.
Thanks again, Mikhail.